Hi, good morning, good afternoon, good evening to all participants around the world. My name is Matt Wargon. I am one of the co-chairs of the American Nuclear Society's Young Members Group Program Committee. I am a nuclear design engineer at TerraPower up in Seattle, and I'll be your host and moderator for today's webinar. Helping me out behind the scenes with logistics and Q&A are Catherine Pratt, Persh Desai, Tim Crook, and Elise Huffman with the ANS Young Members Group, as well as Dan Goldberg from ANS. The ANS Young Members Group is a professional organization within the American Nuclear Society comprised of students and early career professionals that either work in some sector of the nuclear industry or just have an appreciation for what nuclear science, technology, and engineering can do for the good of the world. On behalf of the ANS-YMG, I'd like to thank you all for joining today's webinar and hope you enjoy the exciting content we have planned. Today, we are excited to bring the fourth installment in our Spotlight on the National Lab series, this time focusing on the National Renewable Energy Lab, or NREL. Before I pass the baton to our first speaker, let's go over a quick summary of what we have planned for this session. First, we'll get an introduction from Julia Bisconti of the US DOE, followed by an overview of the lab from Lab Director Dr. Martin Keller, after which we'll hear from 5 lab employees about their unique work. After all of our panelists present, we'll have a Q&A session, during which time I'll ask the panelist questions that have been submitted by you all, the participants. If you hover over the bottom portion of the Zoom window, you'll see an option to ask questions. If you click down there, it just says Q&A, you click on that and you can type a question. We'll be sorting those questions throughout the course of the presentation. And at the end, I'll be asking the panelists selected questions, and we'll try and fit in as many as possible. Please feel free to submit questions throughout the course of the presentation, and we will get to as many as we possibly can. Now, without much further ado, let's get going with our first speaker. Julia Bisconti is a senior advisor in the U.S. Department of Energy, Office of Nuclear Energy, where she leads key multilateral initiatives, including the Nuclear Innovation Clean Energy Future NICE initiative. So now I will pass it off to Julia.
Hi, everybody. The webinar today is co-sponsored by 2 Clean Energy Ministerial or SEM initiatives. These are the Nuclear Innovation Clean Energy Future Initiative, or as we call it, NICE Future, for which I am a lead country team member, and the Clean Energy Education and Empowerment, or C3E initiative, which focuses on gender diversity in clean energy. It's very exciting to welcome so many international listeners today who are here to learn more about the roles that NREL plays to foster clean energy transformations and develop holistic energy options. NREL serves as the operating agent for the NICE Future Initiative and some other SEM work streams. In that role, NREL provides outstanding coordination and technical expertise. It also works closely with the DOE Idaho National Laboratory on this effort, which you have heard from earlier in this webinar series. NREL has a great capacity to piece together the connections across clean energy technologies with important energy integration analysis. So we look forward to hearing today about the breadth of energy work with which NREL is engaged. This includes how nuclear energy plays a key part of that clean energy puzzle. Who would have thought just a couple of years ago that we would be actively discussing the synergies that are possible between nuclear and renewables and clean energy systems? Much of this is thanks to the great momentum that we built with the NICE Future Initiative. Under the leadership of the DOE and our co-leads in Canada and Japan, and with NREL's help, the NICE Future Initiative has grown to engage experts from 60 countries and 80 organizations with the intent to provide technology options to policymakers, explore economics, and provide communication tools. Clean energy transitions are not just about technology. We will also need to rely on a diverse talent pool. So today you will hear from young rising stars of NREL. You will also hear from NREL's US C3E ambassador, who will address how gender diverse workforces lead to greater organizational performance and stronger results. Despite making up 48% of the global workforce, women only account for 22% of the global energy sector workforce. Now, let's hear from NREL. Let's hear about the future of clean energy. Thank you.
Thanks, Julia. Next, I'd like to introduce our first speaker from the lab, Dr. Martin Keller. Martin Keller has served as director of the National Renewable Energy Laboratory and president of the Alliance for Sustainable Energy, the company that operates NREL for the US DOE since 2015. So please give a hand out for Martin Keller. Thanks.
So, Matt, thank you everybody for taking this morning, afternoon, wherever you are, to participate. I'm sorry that I can't be with you in person. I mean, it's really a new world we're getting used to, but I mean, when you see we have over 560 participants, probably if you would be all in one location, might be much harder. So again, thanks for giving us the opportunity to show and highlight a little bit what we're doing here at NREL, and also linking this, and Julia brought this up, there's so much very cool synergy between what's happening in the nuclear energy world and what we're doing in renewables. And we hope to show you today what the synergies is and why in all the above, how important it is that we're looking into this, because there's so much evidence out there right now. By linking all the different elements together, we're creating a better energy future for the future. So with this, let me go to the next slides. I want to give you in the next 15 or 20 minutes a very high level overview why it is so important right now that we're looking on a global scale around what's happening in the energy space. So I want to start out with the so-called megatrends. When you look into this, what's going on our planet, we all know about population growth. I talk with one side about urbanization. There's a lot of food and water issues, and also more and more what we call distributed energy resources. And then there's mobility. And the kind of factor integrating all this together, this big megatrends, is energy. So when you go to the next slide, you're seeing that urbanization is something which is a big issue for us. So can you advance to the next slide? So when you look at this, every week, 2.4 million people on our planet move into the cities. Right now, about 30% of our world population lives in the city. By 2050, it will be over half of all the people live in the cities. So urbanization is the big issue. And then there's mobility. And in mobility, you have seen this, how fast we advanced in 100 years to go from horse carriages to cars. And then the future of mobility is now completely changing with autonomous driving, with all the electrification going on. So we're seeing that urbanization in combination with mobility will change the way we travel around, how we're using energy, how we're building the cities, how do we provide all the necessary resources to the cities. So energy in all these changes will be the key element and the integrator, and one of the big issues we have to get right. On the next slide, you see then suddenly now how, so it might take over a second, yeah, so that we here in the United States, but also on a global scale, there is a transformation of the energy supply happening. So when you look in the next slide a little bit into the details of what we're seeing in the energy transition or transformation, you're seeing that we're seeing a big decline in coal over the last couple of years. We see a huge increase in natural gas, and frankly, this is due that through fracking, that natural gas right now became so cheap, and so a lot of people shifted over from coal, and utilities shifted from coal to natural gas. You're seeing the nuclear is pretty stable. And then you're seeing also down there on wind and solar that we're seeing a huge increase in moving over to renewables energies. So why do we see in the utility sector this big change of moving over to renewables? The next slide shows you a summary of the cost which is associated with some of these energy technologies. Again, a lot of this data goes back to a Lazard study. And when you see right now, nuclear is still in the last couple of years is increasing in cost. And I think this is a big challenge for us. How do we can get the cost of nuclear energy down? Because we will see this in the following slide that nuclear, in my view, also will play a very, very important element in the kind of integrated energy where we need to look into nuclear. Coal stays pretty stable. But then you see how the green line, wind and solar came down significantly. And then when you look into the right segment of the slide, This is the price forecasting for Excel in the last power purchasing agreement. And you can see that even now wind came down to $21 megawatt hour, and this includes 4 hours of storage. Utility scale came down at $36 a megawatt hour, also including 4 hours of storage. So now when you look even the latest prices for some of the renewables, this even now going further down. So we're seeing that a lot of utilities, when they deploy new energy generation technologies, move to renewables because right now they became the cheapest way of producing electricity. But of course also this increased renewables on our grid will also cause potentially some issues, and we will talk about this in a couple of few slides where we're seeing where this is going in the United States. So please go to the next slide. So when you look at NREL at a glance, to give you a very high level, so we have about 2,051 employees. So we have world-class facilities. We have a lot of partnership with industry and academia and government. So per FTEs, we have probably the most collaboration with industry across all the national lab, because we feel that this is the DNA of NREL, to create these collaborations to push technology into the market. And our campus is a living laboratory, so we having a lot of net zero facilities. We're using our facilities also as a living campus to learn how you, for example, work in a net zero facility. The next slide shows you a big overview of our kind of different portfolios. Most of us know us on the renewable power side, so where we've done a lot of work in solar, wind, water, and geothermal, just to name a few. Doing a lot of work in sustainable transportation, everything from bioenergy, vehicle technologies, and a fully integrated hydrogen project, all the way from using new catalyst materials all the way to testing a hydrogen fueling station here on site. On the energy efficiency side, we do a lot of work in buildings, in advanced manufacturing, and also in the government energy management side. And then there is the more fast growing, what we call energy systems integration. So we're looking into this, how do we integrate all this together? How do we link renewables with energy efficiencies, reaching out to, for example, and this is a goal where we have this wonderful collaboration with Idaho National Laboratory. What's the synergy between nuclear and renewables? And we will also talk about this in the high level slide. So a lot of work goes into the energy systems integration. How does the grid of the future look like? How do we develop hybrid systems in our grid system? So on the next slide, you show that we're also working a lot on international levels. So we have more than 80 collaborations on a global scale. We think it's very important to really work on a global scale. And again, this is all the way from helping to model the grid they have, to forecasting what research they have on wind, on solar, for example. So it's a very broad international collaboration with many, many different countries in many different areas. On the next slide, I want to just show you a couple of very high level. A lot of people say, why do we need to continue research in renewables, so wind and solar specifically? We are already now below grid parity. Why do we do this work? There's a lot of work going on solar. We're seeing that solar is just scratching the surface right now. Some of the next materials going into solar research, like perovskites, have the chance to even further decrease the cost of solar significantly. But then there's also a lot of research going on how we're integrating solar into our grid. How do we create it more resilience? How do we improve the overall systems efficiency? So a lot of work still goes on, from very early materials research to all the way uphill, to see how we can integrate solar into the overarching energy portfolio. The same on the next slide is true for wind. Wind is now, right now, in many areas, the cheapest way to produce electricity, but there's still a lot of work going on in wind, all the way from new materials to produce the wind blade of the future, and a lot of work also in more of the reliability of wind, working on the gearboxes, on some of the rotor sizes. A lot of work is going on offshore wind. And I want to show you just on a couple of slides, on the next slide, how increased wind research can even bring wind into many more different areas. So this map shows you the current wind potential when you go to so-called 80-meter hub height on our wind turbines. The next slide shows you how this map is increasing if you go to 110-meter hub height. And then the next slide shows you how we getting these resources distributed across all 50 states in the US by going to 140 meter hub height. So looking at the slide, it's very simple. So why we're not going just to 140 meter hub heights? I don't know how many have seen some of this news. GE has now a new turbine which will be going onto the market in the next 2-3 years, which is, it's a real beast. It's huge, but again, it's only for offshore. So why we're not using the same technology and producing these large wind turbines here onshore? And the answer is very simple, because at this 140 meter hub height, we cannot transport wind blades and the towers to the sites because we are limited by transportation. And again, this is where early stage research comes in to see what about if we make wind blades and the towers on site. Can we use new materials instead of thermoplastics? Can we use thermosets? Can we completely change the way we're making these machines on site? And again, this is where DOE, where a lot of early stage research comes in to work with industry and further expand and explore the wind turbines of the future. On the next slide, you're seeing that this is the same is true for geothermal. So geothermal right now, for many years, it did not move much, but right now there's a big push again in geothermal, integrating it to other renewables, but also then looking into geothermal as an energy source, which we could store a lot of energy with energy storage in the thermal plants. And then also through some of this new drilling technologies, it opens up a brand new venue for geothermal. So we also feel that the link to geothermal, linking this to other technologies, will be a very interesting element for the years to come. So the next slide shows you what we call looking into the future. So where do we go? So what's the next big things on our horizons? So we developed a 10-year vision study for NREL, which we then also use to develop our research plans for the future. And there, at what we call this environmental scan, on the next slide shows you what some of our workshops showed. And this again was done with outside folks coming, visiting us. We did a lot of workshops internally, externally. And when you look at this, what we're seeing is this observational trends reaching out to 2040. So we see that growth of energy use in the developing world will by far outpace growth anywhere else. We see that global renewable power demand will grow significantly. Urbanization, as I mentioned in the megatrends, will grow very, very quickly. And electrification, electric vehicle adoption will grow strongly. But then also the demand for high-density liquid fuel will also grow. So we will need more high-density liquid fuels in the future. And then the 3Ds, digitalization, data, decentralization, will be strong drivers for the energy transition. So the next slide shows you a very high level overview of what we used with this looking into the future, did this kind of 10-year vision plan, how we're seeing some of the big 3 initiatives what we're developing here at NREL. The one is the integrated energy pathways. So this is how do you link all this together between renewables, efficiency, linking, let's say, for example, to nuclear power, even linking to fossils. What's the synergy? How to integrate all these different elements together? How to develop a distributed energy resource for the future? And then there's these 2 little buts coming up. One is what we call electrons to molecules, and I will show it one slide what we're doing in this area. And then also what we call circular economy for energy materials. So this shows you at a very high level, and we try to use the 40 years look into the future to help us to develop some of the big initiatives here at NREL, and how, again, also then in the next slide, you're showing how we're integrating all this out. So what is the integrated energy pathways? So we're trying to develop the foundational knowledge and technologies to optimize the integration of renewables, buildings, energy storage, and transportation, modernizing our energy systems and ensure a secure and resilient grid. So this will be a big effort for the next years to come, how we develop this integrated energy pathways. In the electrons to molecules, again, what I said, we will need more hydrocarbons in the future, but is there a different way to make them? Can you make them in a sustainable and renewable way? So this will be extremely important for the future, for chemical materials, fuel synthesis, and energy storages. And then there's the circular economy for energy materials. We have to completely rethink the way we're using our materials for the future. Right now, we just make our technologies and then we dispose the materials. How can you bring the new materials from a very early stage into this, that we developing and taking the reuse of the materials already in the design phase of the new energy materials of the future. So the next slide shows you a little bit, a couple of slides about integrated energy pathways, what we're trying to develop. The next slide shows you how we're changing the way we're using electricity. In the future, in the past, it was very simple. You delivered electrons to the customers, the customer used it. And now suddenly you're seeing that the grid will become bidirectional. Our houses become much smarter. So we have an electric vehicle in front of our door, which also might be used as a storage element. So we have smart water heaters. We have solar rooftops. So again, the grid is completely changing. And again, this is a challenge for the grid architecture of the future. In addition, on the next slide, you show that we will increase our electricity consumptions. By 2050, we're seeing that we have different scenarios, but every scenario shows that electricity demands will go up, mostly driven by the electrification of our transportation. So the question is, how do we create more electricity? How do we use electricity in a different way? And again, this will be the big challenge for our grid architecture and the way we're running and developing the grid of the future. So the next slide shows you a kind of future energy systems overview. The future energy system will integrate all types of energy systems and be much more complex. It will be more distributed and much more interdependent. And again, we feel if you do this correctly, you can develop the grid of the future, which is more efficient, is resilient, and is also very affordable. But you can see already on this flow chart, the one directional is completely changing to bidirectional, much more complicated, many more distributed ways to bring electricity onto our grid system with very smart houses and communities. And again, this will be the future. How do we manage this future energy system? And again, this is what you will see on the next slide, where we feel that machine learning, autonomous system will play a major role for the energy systems of the future. So we have it the same for power grids, for transportation in the buildings, and on also how, for example, how we've been managing our wind plants. It will be done on autonomous systems and will be done with machine learning, but this will require new math, new nonlinear control systems, new optimization of all the different data inputs. It will be very complex, and we need to learn to deal with this big data analytics to bring all this together in this more autonomous system. And there's also the critical element of cybersecurity, because we feel you can do it right, but cybersecurity in the years to come in an autonomous energy system will be even of more relevance as it is right now. So cybersecurity will increase. The next slide shows you just one very quick element about what we say the electrons to molecules. On the next slide, it shows you the concept where we're going with this. Electricity will be the cheapest way of energy in the future. So how can you link this, for example, with CO2 as a source? And can you capture and concentrate this and create with new conversion technologies through biocatalysis, electrocatalysis, hydroelectric biocatalysis? Can you recover and purify this and create fuels, chemicals, materials, and also storage for the future? Very likely, this will go probably through hydrogen. And again, this is what we're feeling, and the synergy between renewables and nuclear power also can bring a new element into this electrons to molecules. Can we use electricity in a synergy between renewables and nuclear to make, for example, fuels and chemicals of the future? The next slide, circular economy of energy materials. I mentioned already, and the next slide shows you the very high level overview what we're trying to do. Right now, we're doing a kind of very linear approach. So the next slide shows this, where say you take, you make, and you dispose. The future of this will be that we're going in a circular element that you make, reuse, and you return the materials back into our economy. And this will require that the design already of some of these energy elements will bring the reuse into the equation. Best example there right now is lithium batteries. We just designed them to be as energy dense as we can, easy to charge, and so on. But we have not brought in the design element that we want to return all the elements back into a environment, in an economy. Again, this is where in the future we need to approach this differently. The same is true for our solar panels. The same is true for our wind blades, of our wind machines. So we need to bring this circular element at an early stage into the kind of design element. And again, the most, now with DOE is going down, one of the elements where we're starting to do this first is on the so-called plastic upcycling. How can we bring some of the plastic materials back into our economy? We say there's not a lot of aluminum cans floating around in our oceans because we know how to recycle aluminum very well. We don't know and we don't have a good process on plastic bottles, for example. So if you find a way to bring this complex organic molecule, which a plastic bottle is, back into our economy, it will also help in bringing and recycling some of these very interesting materials. So on the next slide, I want to highlight this and set the stage for some of our following speakers also to talk a little bit about Tri-Laboratory Consortium. So the Applied National Laboratories, which is here, NREL, the National Energy Technology Laboratory, NERL, and Idaho National Laboratory, we got together a couple of years ago and asked, how can we really bring and integrate a lot of this energy generation technologies and look holistically around the synergy of all these different elements? So this is all from gas turbine combined cycles, coal and oil, bio-fired production facilities, the nuclear reactors, looking thermal energy, electricity energy, how do we do storage, how can you do the synergy, how can you link all these different elements together. So the next slide shows you some of the synergies between the nuclear, renewable, and hybrid energy systems. And just to name a couple of elements there. So the first, and again, comes back to what we call electrons to molecules. There's liquid transportation fuel. There's a program where we're asking, how could you link this together? How could you use nuclear reactors, the wind power, not only putting electrons onto this grid, but also how could you use this kind of synergy to produce liquid fuels? So the same is when you look into reverse osmosis for desalination. What I told you, but with the big growth on our cities and also especially in the issues on food productions, water will be a major issue. What's the synergy between renewables and nuclear towards producing desalination plants? The big issue right now is in the future is thermal energy. And again, there is, in my view, where nuclear can play a major role by using some of the thermal energy potential of nuclear plants, combine this with renewables and produce the thermal energy, mostly, of course, for industry applications. And then there's again, was that hydrogen productions, which again goes towards liquid transportation fuels. Is there a way where we can use the synergy between wind power, solar power, and nuclear reactors to produce hydrogen in a more efficient way and cheaper way and carbon neutral way? So there's a lot of opportunities in our view to linking renewables and nuclear power for the future. So the next slide shows you the partnering for impact. So how do we do all of this? We have a big challenge in front of us. So we go on the next slide showing that we need to bridge this gap between universities and some of the very fundamental national laboratories and go towards corporations, how to bring technology into the market. And this again, where we feel that the applied laboratories like Idaho, NERL, and NREL will play a major role to try to bridge this gap and bring technology into the market. So the next slide shows you a couple of high-level partnerships we're doing with ExxonMobil, and Idaho National Laboratory is also part of this team. We're doing a lot of work with Shell. EATON Corporation is in our facility, which is doing a lot of electrification of transportation, and also EATON, you probably all know EATON, your circuit breaker very likely comes from EATON in your house, in your apartments. And again, the next future is how do you integrate this together? And then we're doing a big program with Wells Fargo, just to name a couple of our industrial partners, again, with this goal to push technology into the market. So I want to stop here and next slide, thank you for your attention, and I hope that we have time for questions down the road. So thank you very much.
Thanks, Martin. That was a great presentation. I can't believe GE has 140-meter tall wind turbines. That's crazy. Our next speaker will be Dr. Jill Engel-Cox. Jill is the director of the Joint Institute for Strategic Energy Analysis, JISEA, at the U.S. National Renewable Energy Lab. So Jill, if you're ready, I'll pass it off to you.
All right, thank you very much, Matt, and very happy to be here. In my few minutes, I'm going to talk a little bit about the analysis that NREL does, including some of the work that we do at JICEA related to renewables and nuclear. So if you go ahead to the next slide, as Dr. Keller showed us that we're really undergoing a pretty significant transition. So if you look in the US with hydropower, renewable energy is over 17% and growing. And if you add in nuclear, which is about 20%, the US low carbon electricity is 37%. And I think this number surprises some people sometimes because we're really making rapid progress towards this. And this is not just in the United States. We're seeing these types of transitions going on in many countries around the world. But it's very important to understand and model how these technologies work together. So if you go to the next slide, one of the key things that we do at NREL is that we're looking at different electricity models over different geospatial and timeframes. And looking for the next slide, if you can get there. And there we go. So we look at electricity modeling at multiple scales. So all the way from the generator scale, so at the individual power plant level, as well as how customers and those who use energy would operate and behave that affects that demand side. So the demand is, we've been talking a lot about generation. The demand side is also very important. And then we have models that go through the regional scale, the US, the country level scale, and then all the way on up to the global scale of how you model the way this transition may happen. And then you have to look at the time scale. So looking at setting goals at sort of these annual levels of how we may want to see different types of energy sources in our system, all the way down to the hourly and sub-hourly in terms of how these technologies actually work on a grid or with an industrial plant or other types of facilities. So if you go to the next slide, we take these models and we look at future scenarios. So it's very difficult to predict the future. None of us really predicted the rapid advance of natural gas and the rapid advance of renewable energy in the last 10 years due to different technology and policy elements. So the way we approach that is we look at a variety of different scenarios. And we have these are some examples from our standard scenarios report where we look at options where we might have very sort of renewable energy prices not declining any further, continuing to have low natural gas prices, all the way to very low renewable energy prices and natural gas prices going up significantly for some reason. And then what you see on that chart is the variable renewable energy penetration. So when we say VRE, variable renewable energy, we're primarily talking about wind and solar, as compared to hydropower or geothermal, which are more dispatchable energy sources. One of those scenarios does look at a reduced cost nuclear generation, which is there on the bottom left. And that could be reduction in cost with our current existing fleet, but more likely it could be advancements in small modular reactors that enable us to have lower price nuclear power going forward, and how that might change different scenarios. The map on the right also shows that it's important to look at the geospatial element of this. Because different parts of the US, being a large country with different types of resources and different existing infrastructure, may have very different scenarios in energy sources going forward. So you can see California in this mid-case scenario could be 50% solar. California currently is 19 to 20% solar. So they're already well on their way towards that goal. Texas could be 40 to 50% wind. That would be similar throughout the middle part of the US. And then the Southeast would potentially be 25 to 30% nuclear power, given their current existing fleet. So it's important to think about the locations and understand that there's not one solution for all locations. And this includes both from a state, subnational perspective as well. When you look at different countries around the world, we'll have different solutions depending on their resources, their capacities, and their social decision-making, where they want to be as a society. So if you go to the next slide, this is showing how we actually do some of this modeling on an hourly basis. And if you click again, it'll hopefully start the animation. And there we go. And what's going to happen here is you're going to see the sun come up. And as the sun comes up, you will see a lot of yellow. That is the solar generation being created. Nuclear is in the red circles and wind is in blue. And then the lines, the arrows going is showing the transmission, how we need to transmit power from locations that have more energy versus less. And as you see, the sun just went down there, and you can see often we have an increase in wind in the evening, and you'll see nuclear and coal-fired power plants generating power. So this is just an example. There's a number of these types of videos on YouTube if you'd like to see how this works. And this is really just showing that we are doing the modeling to look at how the grid could actually accommodate different levels of renewable energy and other power sources over time. If we're going to look at 70% renewables at some point in the future, variable renewables, we have to know that our grid can actually operate at that scale. So if you go to the next slide, I'm going to, this is a little bit about the Joint Institute. And the Joint Institute for Strategic Energy Analysis, we actually look at these different systems. So systems integration, how these systems might work together. And that includes with non-renewable systems. So nuclear and fossil fuels, we look very extensively at how those intersect with renewables. We look at how clean energy could go into new systems such as industry and agriculture, as well as manufacturing. And then we focused significantly on international collaboration and capacity building on how other energy systems can move going forward. So if you go to the next slide, I want to talk briefly about our two Clean Energy Ministerial programs that we operate for the Clean Energy Ministerial. The SEM is a partnership of the ministers of energy around the world. And the 21st Century Power Partnership is focused on helping countries achieve clean, reliable power systems. And we help them look at their tools, do capacity building, help transfer some of these models that I've showed you to different countries so they can operate them to understand how they can make choices around different energy options, both renewables and nuclear and fossil fuels, and what might work best for their system. If you go to the next slide, the other program that we run for the Clean Energy Ministerial is the Nuclear Innovation Clean Energy Future, or NICE Future. And this is the one that Julia mentioned, and my colleague Jordan Cox is going to talk next about some details around some of the technical work we're working with NICE Future. But NICE Future is a global partnership of countries that are looking at the potential for nuclear power uses and innovations and systems integration, particularly with renewables, to look at progress towards clean energy goals. So the lead countries are the US, Japan, and Canada, as well with significant participation by the United Kingdom, and then you can see other participant countries there, and then a variety of different international partners. And we do a combination of things from education to webinars. We do a wide variety of webinars looking at youth and education, as well as to look at encourage students and young professionals to look at clean energy as a future option. And then we're also doing a variety of technical integration studies. So I encourage you to sign up for the NICE Future mailing list, because we do have a wide variety of programs that we support around nuclear energy as part of the clean energy future. And we are happy to collaborate with Julia and our colleagues at Idaho National Lab and other partners to go forward on this program. So that's just a quick summary of some of the analysis that we do. And Jordan's going to talk a little bit more about NICE Future, some of the technical work that we're doing in that program. So I will, I think we can go ahead to the next presentation then.
Thanks, Jill. That was some phenomenal data visualization. I really, really enjoyed that. Next, I'd like to introduce Dr. Jordan Cox. Jordan Cox is currently a postdoctoral researcher at the National Renewable Energy Laboratory, focusing on techno-economic analysis of energy systems for economic and resilience applications. And I'd also like to note that Jordan has been a member of ANS since 2014. So take it away, Jordan.
Hi, everyone. Thank you, Matt. My name is Jordan Cox, and as Matt mentioned, I'm a postdoctoral researcher at the National Renewable Energy Laboratory. In the couple of slides I have today, I just quickly want to emphasize two things. Firstly, some of the background and work we are doing for the Nuclear Innovation Clean Energy Future Initiative, and also to really emphasize that for people on this call who are considering different opportunities of employment, national labs are pretty great places to work. I'm going to explain that. So we can go ahead and move into my slides, and we'll we'll go from there. So first, I'm just going to start really quickly with a background of my research. So as Matt mentioned, my research, I actually received my PhD in nuclear engineering, where I was researching gas-cooled reactors. But as I finished up my PhD, I was very interested in not just the physics of how nuclear reactors operate, but also the economics of how power systems work. So I accepted a position with NREL to do a postdoctoral research position on specifically the economics of energy systems. And at NREL, we do a lot of work internationally, as we'll talk about with the NICE Future Initiative. But I just wanted to quickly share one example. This picture here on the left is actually from last year. We traveled to the country of Morocco and worked with the Morocco National Office of Electricity to listen to and understand some of their energy needs and perform some techno-economic analysis of how they could meet their energy needs in the future. And as Dr. Jill Engelcox mentioned, we do a lot of long-term planning to basically understand, as people have energy goals, particularly clean energy goals, how do we meet those in a cost-effective and reliable manner? Is really a thing that we focus a lot on at NREL. And with the NICE Future Initiative, I think it's really important. I want to emphasize before diving into the technical work, a lot of people ask me, why are you at NREL? NREL is the National Renewable Energy Laboratory. Your background is in nuclear. Why are you here? And I really just kind of like start with that sentence by saying, I love all forms of clean energy. My career is really focused on how do we work between all energy sources that are capable of providing clean energy to provide clean energy for our entire economy. And nuclear definitely has a role to play with that, as does variable renewables, as does, for example, fossil fuel with carbon capture. And I really appreciated Dr. Keller's remarks around the interlaboratory work surrounding this, because I think the days of laboratories kind of working in silos is very over. And if we're going to see the type of deployment we want for all of our clean energy technologies, we really have to work together. And I really love organizations and programs like the NICE Future Initiative for that, because it's very visionary in stating this need to work across sectors in order to achieve clean energy. So we can go ahead and go to the next slide. For the NICE Future Initiative, I really want to focus on the flexible nuclear campaign. So most of my work, or a chunk of my work, is the technical lead for NREL on the flexible nuclear campaign. Underneath the Clean Energy Ministerial, which is an international organization devoted to clean energy, there are initiatives like the NICE Future Initiative, and each initiative is kind of a long-term project that can result in smaller term chunks of work that are called campaigns. So the flexible nuclear campaign is really focused on bringing about recognition of the role that flexible nuclear energy can play, or the roles that flexible nuclear energy can play in clean energy systems. In order to emphasize kind of the collaboration we have with other laboratories, I actually am borrowing, and thank you Idaho National Laboratory for this graphic, that I think is really key. So, today we really focus a lot on electricity when it comes to clean energy, and both from a nuclear and renewable scale, some of the things that have gotten the most attention are the deployment of clean energy. In the future, we will probably see widespread deployment of lots of clean energy sources, but these energy sources are going to have to do more than they've ever done. So transitioning from an electricity-only system to things where our energy systems are providing industrial thermal power, hydrogen for electric vehicles, and clean water and process energy is really something that we need to do. And particularly our friends at INL, and again, emphasizing that cross-laboratory work. I don't do nuclear research specifically anymore. I do a lot of stuff work surrounding nuclear, but when I have questions for nuclear, I just call up INL because they're the best in the world in that. And that cross-laboratory research between INL and PNNL and Argonne and NETL is very, very important these days for how laboratories work. So INL is doing a lot of work to understand and research large light water reactors, so the existing nuclear fleet and how it can provide flexibility, small modular reactors, microreactors, and advanced reactors, and how all these things can provide flexibility. And we're working together with INL and with other countries, as Dr. Engelcox mentioned, around what are the needs for flexibility, particularly as countries strive to meet some of their lowest cost energy with variable renewables, and how can nuclear play that role? How can it provide flexibility or provide multiple roles to clean energy systems? We actually have our first report coming out for the Flexible Nuclear Campaign soon, and so look forward to that. But the Flexible Nuclear Campaign really is this international initiative to bring kind of recognition to flexible nuclear energy and its potential roles in clean energy systems and how it can partner with other energy sources. And it's pretty cool. We can go ahead and go to the next slide. The final thing I want to mention in my presentation is just life at a national lab. For people who are on this call who are considering where they work, I just really want to emphasize how cool national labs are as places to work, whether that's other national labs or, NREL, where we obviously really love. They're really great places to work. I myself appreciate a lot the inclusion and diversity at national laboratories. So I'm part of the LGBTQ+ network at NREL. And additionally, I'm part of the NREL Climbing Club. I think Grant Buster is as well. But just really to emphasize that national laboratories are places that appreciate diversity and appreciate inclusion in the way that they conduct their business. I also wanted to just provide quickly, you can see at the bottom here, my email and Twitter handle. I'm a postdoc, and so I'm doing my best to kind of collaborate with people outside. Please feel free to reach out and contact me if you have ideas for collaboration or want to learn more. Also, the Nice Future Initiative, you can reach out here. And with that, I'll go ahead and end my comments and turn my time over to Grant.
Thanks, Jordan. I'm really jealous of the NREL Climbing Club. That sounds like a lot of fun. Next, I'd like to introduce our next speaker, Grant Buster. Grant Buster is a member of the Data Analysis Tools and Applications Group in the Strategic Energy Analysis Center. His work focuses on creating and analyzing NREL's state-of-the-art renewable energy resource data. And Grant is actually a former engineer for NuScale doing probabilistic risk assessment. So another former nuclear employee. So take it away, Grant.
Thanks, Matt. Could you go to the next slide? So my name is Grant Buster. I'm an engineer at NREL in the Strategic Energy Analysis Center. I was told that a lot of our audience will be people in university or college, so I figured I should give a brief overview of the trajectory that led me to NREL. So I studied mechanical and nuclear engineering, and it was awesome. I got an opportunity to work at NuScale Power in the probabilistic risk assessment group. In that group, I did systems analysis. I ran codes like RELAP and Melcor. So shout out to all the nuclear engineers that run RELAP and Melcor. They're really like the best way to learn how to do systems analysis. I mean, they're fantastic modeling codes. At NuScale, I got really interested in the simulation modeling aspect of research, and specifically the data modeling side of things, and kind of programming and automation and big data analysis. So that led me to NREL, where I'm doing data engineering and data science. So I work on a huge range of tasks all the way across the spectrum between data engineering and data science. Today I'll be mostly talking about just the data and what we do with it, some of our studies that we've used or that we've done. So next slide. So this is the National Solar Radiation Database. This is NREL's flagship solar resource data set. So what you're actually looking at is the solar resource, the solar power at the surface of the Earth. And this is a really cool data set. It's historical, so we've got 21 years of data, and we're generating new data every year. It's a huge data set. The full data set's, I think, around 60 terabytes, and we're generating maybe 20 to 30 terabytes of new data every year. Now that alone shouldn't be impressive. Any random number generator can make 20 terabytes of data. But the cool thing about the NSRDB is that it's actually historical data. So we actually take historical atmospheric data from a NASA reanalysis data set, and then cloud data from satellite imagery. And then we run it through radiative transfer models on our supercomputer here at NREL. And that gives us irradiance at the surface of the Earth. So a pretty cool data set. Next slide, please. This is our wind equivalent. So the Wind Integration National Dataset Toolkit, or just Wind Toolkit. So what you're looking at here is a particle flow simulation at 100-meter height above the surface. So this data set has all sorts of rich data. I mean, wind speeds, wind directions, precipitation, humidity, all sorts of other wind data. It's around 6 years of data at 5 minutes. And it's actually a massive data set. This one's around 400 terabytes. So this is a really cool, rich data set. So what are these data sets actually used for? Well, they're public data sets. So anyone in the world can actually go online and download the data via our websites, or programmatically via APIs, or access these data sets on the cloud. So the funny thing about these is that, I work with them, I produce them, but I don't know half of what they're used for. Next slide. I work in the Strategic Energy Analysis Center, so I can speak to some of the things that we use these datasets for in our strategic energy grid integration studies. So these are just 3 of the studies we're doing in SEEK. We're doing a lot more studies, but these are some of the high-profile ones that I've been involved in. So the North American Renewable Integration Study, or NERIS, is, well, you might know that Canada, US, and Mexico are all on different grids, and you can't really trade electricity back and forth very easily between the 3 countries. NERIS looks at, or is studying what a grid would look like if you integrated those 3 grids and then developed high penetrations of renewable energy. We're also doing an extreme weather event study. So as our grid, or as the cost of wind and solar fall, and we get to higher and higher penetrations of renewable energy, our grid becomes more intertied with weather and extreme weather. So we're looking at, or we're studying grid resiliency with respect to extreme weather events, such as polar vortexes, hurricanes, and just other kind of normal events like wind droughts or wind surpluses, stuff like that. Finally, NREL is the research partner for the Los Angeles 100% renewable energy study. So Los Angeles is currently looking into how they could get their grid to 100% renewable energy. And NREL is helping them do that. So it's kind of just envisioning the future of the Los Angeles grid. So that's all I have for today. Thank you guys so much for listening, and feel free to reach out with any questions afterwards.
Thanks, Grant. Next, we have Mark Ruth, Hydrogen Specialist at NREL. Mark is the manager of the Industrial Systems and Fuels Group in the Strategic Energy Analysis Center at the National Renewable Energy Lab. So you're up, Mark.
Mark, you're muted. I got a phone number in. We can hear you. Okay, can you hear me? Good. Okay, great. Good afternoon or morning or evening, wherever you are. Thank you, Matt. Thanks for this opportunity to speak a bit about some of the work that we're doing in this space. I'm going to speak specifically about what we call the H2 at Scale initiative, which is the Hydrogen at Scale initiative, which really thinks about hydrogen as an energy intermediate that can support both decarbonization of energy demands as well as increase the carbon-free energy supplies on the system. If we go to the next slide, please. So here on this slide, we show on the left the H2 at Scale initiative as we think about it. And as I said, I really think about hydrogen in this case as being an energy intermediate, because you can produce hydrogen via electrolysis from a lot of different sources, via electricity, or you can utilize, say, renewable natural gas or other resources to be able to produce carbon-free or net carbon-free hydrogen directly through steam methane reforming. And once you get that hydrogen, which is shown in the blue ball, then you can go to a number of different difficult to decarbonize demands for that hydrogen. Today, hydrogen is used pretty heavily, in fact, very heavily. Almost 2% of our total energy use in the U.S. goes through hydrogen primarily for oil refining, about half of it, and another half going to ammonia production to be able to produce fertilizer for producing crops and foods and other things. However, because hydrogen is such an interesting molecule and is such a great energy carrier, there's a lot of other opportunities for it. Probably the lowest value opportunities for it are just converting it to be able to produce heat. But when I start to look at analyses that talk about how to do 80% reductions in greenhouse gas emissions, it seems almost impossible to reduce some of our high temperature heat requirements for industrial applications, for example, without using hydrogen. The next lowest one is power generation. There's been questions during this discussion around how do we deal with power generation base load requirements. One of the ways to do that is seasonal storage. Hydrogen stores very easily for very long periods of time, or relatively easily for very long periods of time. Right now we have 3 geologic caverns storing hydrogen within the U.S., primarily for use on the hydrogen demand systems for refining and ammonia production. However, they could be utilized and new caverns could be built very easily to be able to provide that seasonal storage. So when wind and solar are very prevalent and loads are low in spring and fall, you could store energy and then utilize that energy in the summer and winter when loads are higher. Likewise, there's a number of other additional options for hydrogen utilization. Hydrogen vehicles are starting to grow. We've seen a few light-duty vehicles on the road and more heavy-duty vehicles, which have very, very long time drive cycles. So in other words, you have 2 shifts running a vehicle straight through at a port in a drayage type application where they're removing imported materials and taking them to warehouses and taking materials back from warehouses to the ports themselves. They run 16, 18, 20 hours a day, need fast refueling times. The hydrogen is a great application for those. Likewise, hydrogen can be combined with carbon dioxide to be able to produce chemicals and fuels, and it can be used to upgrade oil and biomass to be able to get to other liquid fuels. In addition, there's a lot of work right now on other end uses for hydrogen. Metals refining is a key one where we can reduce our emissions, both carbon and other pollutant emissions, to be able to produce steel and other products. So how does this fit into, say, the nuclear reactor world? On the right, you see an image that Martin Keller also showed within his slide deck. And what it really shows is what we call a nuclear hybrid energy system. In this case, the nuclear reactor is running full-time, 8,760 hours out of the year. And the difference between the way we run the reactors today and in this proposed system is that today we then run it through the balance of plant and produce electricity all the time. Or potentially we ramp down the electricity production when the total load for electricity is lower. However, that doesn't really reduce costs. It just reduces the electricity output. In this case, we're proposing that when the electricity load is low or the price is low, instead the energy goes to these high temperature electrolyzers. High temperature electrolyzers are state-of-the-art, very efficient electrolyzers for water splitting to be able to produce hydrogen and oxygen. And they're more efficient than low temperature electrolyzers that use electricity exclusively because they can utilize hydrogen as they can utilize thermal energy as one of their energy sources. That operating at a higher temperature, utilizing the thermal energy, increases their overall efficiency and increases the amount of hydrogen produced, or the amount of hydrogen per unit of energy in, thus, in theory, reducing the overall cost of hydrogen. These high temperature electrolyzers give us a nice opportunity to be able to utilize hydrogen production to be able to then support nuclear reactors that currently exist and potentially future reactors. Analogously, you could think about solar and wind and solar PV and wind, or what Jill called variable renewable electricity, in the same way. They probably wouldn't use high temperature electrolyzers, but low temperature electrolyzers that could produce hydrogen when the value of electricity is low, and then produce and then allow the electricity to be sold to the grid when its value is higher. But thinking about today's nuclear reactor, we'll move to the next slide to an analysis that we have going on right now, or I've just completed in partnership with the Argonne National Laboratory, the EATON National Laboratory. In this analysis, the question was, how might we, or what might happen if we utilize an electrolyzer connected to a nuclear power plant to be able to run in this hybrid way? Would it increase the value or maximize the profitability of that nuclear power plant? To be able to understand that analysis, Argonne National Laboratory did the hydrogen market assessment, and they looked nearby to that nuclear power plant to what the different hydrogen demands might be. They analyzed what the price point for those hydrogen demands might be. So if it's competing against current hydrogen demands, or if it's a new product, for example, if you're running buses on hydrogen, what price point does that hydrogen need to be at to be able to convince the fleet operator to convert buses over? And then they developed demand curves, as you can see in the upper left there. In the lower left, NREL worked with the utility to think through what the market price might be in the future. We used our modeling capabilities that Jill spoke about earlier in terms of reads and plexus to be able to come up with hourly electricity prices, looked at the variability, the spikiness, and what might happen within those hours. And then we both gave that information and worked with the Argonne National Laboratory to do a techno-economic analysis and optimization. What they did was they tried to look at a number of different parameters and then determine what is the most profitable configuration of the nuclear power plant and electrolyzer size within it to be able to understand for different situations what might be the level of profitability or the net present value within it. And some of those results are shown on the next slide. So on this slide, you can see that what we looked at was 3 different variables: the size of the hydrogen market, which got to what price it could be sold, the hydrogen could be sold at because of those demand curves; the amount of storage capacity, which really thinks about if you need to be able to provide hydrogen 24 hours a day, 7 days a week, how much storage capacity do you need? And then the electrolyzer size. Given those, given the electricity prices that NREL generated, given the other key input parameters, we then did an analysis and an optimization looking at the profitability or the net present value. And we found that the profitability is obviously very dependent upon the hydrogen prices as compared to the electricity market prices. Obviously, the higher the ratio you have, like a spark spread, the more hydrogen you might want to produce. And then optimization involved aligning the electrolyzer size with the hydrogen demand and properly sizing the hydrogen storage to be able to turn it on and off. If you click on the next slide button, we'll see a little bit, another bullet that really shows that our key finding was around the potential to substantially increase the current profit margins. This utility is now looking at the technology, doing some more investigations, and has started working on a pilot of this type of technology to be able to identify what might happen and if they want to move forward in terms of going through the regulatory process and then installing the electrolyzer technology. At the same time, if you hit the forward button again as well, please. At the same time, the 3 laboratories are going back and saying, well, in this analysis, what we did was we assumed that that removing electricity from the market and producing hydrogen instead would not impact the electricity price on the market. However, we know that that's not very true. So what we're doing now is we're trying to co-optimize the hydrogen markets, the nuclear system design, as well as the operation of the nuclear power plant and the grid operation. So what other generators might make up the change in the generation due to this plant. And then identify what happens there, how that impacts the market prices, and be able to further understand what the NPV might be. So this is a very exciting project, both in terms of the opportunity to introduce new carbon-free energy sources within the energy sector, beyond just the electricity sector within the US, as well as intellectually trying to really understand what happens and when, and how might all these co-optimization challenges fit together to be able to come up with the most economic and optimal solution for the system as a whole. With that, I will turn it over to our next speaker and let them address additional topics.
Thanks, Mark. That was really interesting. It sounds like we have a lot of options in the future to further diversify and make a more reliable grid. Our next and final speaker, I'd like to introduce Dr. Ellen Morris, the Director of University Partnerships and C3E Ambassador at NREL. Ellen Morris is a world-recognized expert on energy and international development with a particular focus on policy analysis, research, strategy development, and writing on energy access, gender equality, and business models for the base of the pyramid. So with that, I'll turn it over to Ellen.
Thanks very much, Matt, and thank you all for having me. As was mentioned, I'm leading up a new program at NREL on university partnerships. And my career path has been anything but straight, having come from studies in geophysical engineering to oceanography to a long career that was mentioned in energy access in the poorest countries in the world, to where I am now at NREL leading up this new program. So if I could have the first slide. So keeping in mind that the research happening at NREL is informed and strengthened by the talent and facilities at universities, we aim to build and deepen those engagements. In NREL's forward-looking 10-year strategic plan that Martin discussed, the universities are key to helping drive where the research is headed in these 3 key areas. Integrated energy pathways, which is NREL's key strength, focused on research that maximizes and leverages the value of existing power systems while integrating renewables, building loads, thermal energy, energy storage, and transportation to create a highly resilient and secure energy system. And 2 other areas that are driving our forward-looking plan are the circular economy, looking at new ways to bring together design, recycling, reclamation, and reprocessing to rethink energy relevant and energy intensive materials, processes, and technologies. And then finally, electrons to molecules, or the electron foundry that uses cheap electricity to convert water, carbon dioxide, and nitrogen to generate high value added molecules that can create new fuels, energy storage molecules, and chemicals. So currently at NREL, there are $42 million right now in research contracts with 95 universities working with NREL that bring unique skills and facilities to help support our research agenda, and also create talent pathways for leading faculty and students from around the world. This includes ways we work, including joint appointments for faculties, postdocs, internships, research collaboration, workforce development, and many more ways that we engage with universities. Next slide. With the University Partnerships Program, NREL is leveraging the myriad assets that we have to bring to a partnership with the university, including our unique mission, our high caliber basic and applied research, the state-of-the-art facilities and campus that we have, the visibility in national and global networks, and close ties to government, industry, and market leaders in the US and abroad. And in turn, universities are helping NREL forge stronger and more visible ties to education and academia to further NREL's research and create a talent pipeline for the next generation of innovators in the clean energy research and technology field that all of you are coming from. And there are three basic elements to the University Partnerships Program. The first is our flagship program that includes 5 universities: Massachusetts Institute of Technology, Stanford, Colorado State University in Fort Collins, University of Colorado in Boulder, and Colorado School of Mines in Golden, Colorado, where NREL is located. These universities play a key role by serving on NREL's board, providing input on our research agenda, and engaging also in research across NREL. And of course, the 3 Colorado universities that I mentioned have been the most actively involved in our Alliance Partner University Program, most likely due to their close proximity to NREL. Secondly, we have the Strategic Partner University Program. And this was created because we feel it's an opportune time to expand the breadth and depth of NREL's strategic engagement with universities. We are in the process of bringing in a cohort of 5 to 10 leading universities from the US that are at the forefront of research and instruction in technical areas that are aligned with NREL's forward-looking strategy that was just described, that will help augment the skills, facilities, tools, and analysis that are happening at NREL. And then finally are the cross-cutting initiatives, which really captures much of the work that's being done to build the strong foundation and the various dimensions of the program. And this includes, for example, expanding opportunities for faculty and students to work at the lab, improving outreach and increasing visibility of NREL in the US and around the world, leading student competitions, industry connections, improving training, and many others that allow for creative and innovative ways for us to develop partnerships with universities. And one key aspect that I just want to quickly mention is how I'm working to build new connections with top-tier historically Black colleges and universities and Hispanic-serving institutions. They have been typically excluded from the mainstream of basic science and engineering, research, and collaboration, and we are interested in trying to build those connections at NREL. So NREL is investing wisely to attract the best and the brightest in a way that's more inclusive. And we are building out this program with HBCUs and HSIs to facilitate high-quality research, competitive academics, student success, and a forward-looking vision to leverage the assets at NREL. Next slide. Now I want to talk briefly about the C3E initiative that Julia Visconti already mentioned in her remarks. C3E, the Clean Energy Empowerment Initiative, is an important initiative that was created in 2010 at the first Clean Energy Ministerial to advance women's participation in the clean energy sector. I serve as an ambassador to C3E, and I've had the privilege to see C3E grow and thrive over the past 10 years. As was already mentioned, C3E seeks to address the gender gap in the energy sector by increasing the participation, leadership, and success of women in clean energy. Next slide. And C3E has 4 pillars that support this initiative. C3 ambassadors are an important and core element of the C3E. It's comprised of more than 40 executives, academics, and thought leaders who serve as role models and advocates for women in clean energy. In their role as an ambassador, we work strengthening the recruitment, retention, and advancement of highly qualified women in the clean energy sector. One of the signature efforts of the C3E is that every year the C3E awards recognize 8 mid-career women who have demonstrated outstanding leadership and accomplishment in clean energy, as well as 1 senior leader for a Lifetime Achievement Award. And we are in the process of evaluating those nominations as we speak. The awards are presented at the annual C3E Women in Clean Energy Symposium and Awards, which explores how women in business, government, law, academia, and other sectors are advancing clean energy. The symposium also importantly builds a strong and interconnected network that continues to grow. This year is the 9th C3E Women in Clean Energy Symposium and Awards that will be taking place on December 7th and 8th at MIT in Cambridge this year. And I would encourage you, if you're interested in attending or interested in C3E or anything else I've mentioned about universities, please feel free to reach out to me for further details. Thank you very much, and I look forward to the questions.
All right, thank you, Ellen. So now I will ask all of the speakers to turn on their cameras and sound, and we will get to the Q&A portion of this webinar. Okay, so to start, the first question is for Martin. It is generally assumed that energy demand will increase all around the world as time goes on. With COVID-19, we have certainly seen the possibility of a lower demand world. What are your thoughts about structural changes from this pandemic in terms of global energy infrastructure?
Thanks, ma'am. That's also an excellent question. So look, I mean, we just can look a little bit into the future where you look even here at NREL, we have a lot of discussion is we realized that a lot of people are extremely productive working from home, for example. Do we in the future all need to go into the car to sit in a cubicle, or can we continue to build on to our experience right now that you can work from home? And this clearly has a direct impact on energy. But this said, honestly, I think that on the long run, no matter what we will do, we will see an increase in energy demand globally. Hopefully we could buy more time to see how can we use this to advance or bring new energy generations online, which hopefully are more on the carbon neutral side and also good for our climate and environment. So, but I don't know, honestly, on the long run, if COVID-19 or the lessons learned of this will significantly decrease the energy demand for the future. I mean, I think there will be a lot of studies done, and I think it will be very, very interesting. But I tell you, even for meetings like this, it's great. Look, we still have, I think we'll see 520 participants on there. We probably wouldn't have this if we all would sit in one room. This said, the social interactions, being at some of the meetings, is something which I think we as humans might tend to go back to having some of these meetings also live. We might see more linkages between online and live meetings. But overall, on the long run, I think that energy demand on our planet will go up.
Awesome. Thank you for that really well thought out answer. Our next question is for Jill. Could you address how we can have a grid of the future with renewables, flexible baseload like nuclear, and other low carbon free technologies, especially as states and local communities in the US and countries around the world look to reduce their carbon impact?
Thank you for that great question. As I mentioned before, I think the energy mix is going to really vary place to place, depending on resources and infrastructure. And so each location, there are countries now that are very high levels of renewable, especially if you count hydropower and geothermal, plus as we're seeing the increase in solar and wind going forward. So I think it's going to be very place dependent. Countries like France are going to have significantly levels of nuclear, as well as they're increasing their variable renewables. I think the key is that the diversity is going to be very important so that you have different energy sources to meet different demands. Also, you're going to have to meet seasonal demands and different scales. So some of our models have shown that we can get to 50, 60, 70% of variable renewables. It's going to be that last 20%, last 10%, and then that last 5% that's going to be much more challenging. And so that's where solutions such as hydrogen, electrons to molecules, storage that happens both hourly and seasonal are going to become very important. So again, it's that diversity and energy mix that's going to be important. And then real briefly on the nuclear side, I think what we're going to see is that if we start to go to small modular reactors, as those technologies develop, it's going to be, they will be allowing a level of flexibility to accommodate this very diverse and flexible grid that we're going to be requiring going forward. And I think that's really going to be the future of how renewables and nuclear are going to work together.
Awesome, thank you. Next question is for Jordan. How do you predict the energy portfolio out to 2050, and what value does that prediction provide?
Thanks, Matt, for that question. Energy predictions and energy models are always imprecise to some degree. And so the way we predict them is essentially looking at the cost of energy sources now, and then we do kind of a scenario-based approach, imagining, well, maybe those costs go up, maybe those costs go down. And of course, that's supported by kind of realistic trends that we're seeing, right? So like natural gas is a good example of things that we see have a large effect on the deployment of different energy technologies. And we look at their historic fuel prices and some predictions about supply. You know, a lot of the infrastructure surrounding things like natural gas take years to build. And so we can get some information about the future of what those prices will look like. And then we look at the demand. So we basically take, for example, REEDS, the Regional Energy Deployment Model, really looks at different demand at peak times throughout the United States, and it matches those with supply. So, you know, for example, we apply constraints like solar energy can meet demand during the day, you know, maybe wind and natural gas and nuclear are great sources at night. And then we use different optimization algorithms to try and reduce the cost of the overall system and come with the lowest cost methods to meet demand. All these models, as I said at the beginning, are imprecise in some form. But what they help us to understand is kind of the choices we can make now surrounding energy policy and energy technologies. So for example, with the NICE Future Initiative, one of the things we're really looking at is, you know, what are the choices people who are designing nuclear systems can make today to have the largest impact on the energy grid of the future? As part of the Flexible Nuclear Campaign, NREL will be conducting some analysis surrounding if nuclear is flexible, what higher percentages of deployment can it achieve versus maybe an extremely low cost scenario? And so these scenarios help us to reduce the uncertainty, but also make decisions around innovation and technology and policies that influence our energy system in the future.
Great, thank you very much. Our next question is for Grant. What applications of machine learning are you most excited about in energy analysis?
Thanks, Matt. Yeah, I think there's tons of applications of machine learning in energy analysis. I didn't touch on them, also because they're not like visually appealing. But I think there's so many projects that we're working on right now. For one example, I'm working on a geothermal project with a New Zealand group. So they have these crazy complicated steam fields, and they don't have any digital twin models to model these steam fields. And so what we're doing is we're developing our own systems model that's kind of similar to like a RELAP or MELCOR in the nuclear space. But for geothermal plants, and they're data-driven. So instead of trying to physically model every physical relationship using scaled validation experiments like you would in the nuclear industry, we're using historical data to build machine learning models that can predict these plants. And then because they're so complicated, these plants are crazy. The amount of experimentation that you can do once you have a digital twin is vast. So there's a few different types of machine learning, and I think reinforcement learning, where you build a machine that kind of experiments in this environment and learns how to operate the system and optimize the system. I think there's a lot of potential in that space.
Great, that's super interesting. I bet that that sort of modeling could really be useful for predicting nuclear maintenance for current and future reactors as well.
Totally.
Next question is for Mark. How do hydrogen and electric vehicles compare when looking at low carbon transportation options? Will they both need to play a role in the future?
So what we found with hydrogen and electric vehicles today is that each has its own role and its own place. And so I think the real question on will they both play in the future depends on what predictions you might have about the future. By that, I mean, right now, as we look at where hydrogen vehicles have had their greatest market penetration, what we have found is, or what we have seen is that material handling equipment, especially equipment inside of refrigerated warehouses, is the best application for hydrogen fuel cell vehicles today. The reason why those are great applications for fuel cell vehicles today is that they're running 24 hours a day, 7 days a week. They need very fast refueling times, and they need to be able to run in a very consistent way. As batteries start to wear down, the lift goes a little bit slower up and down and causes challenges there. So that's an ideal application where you can really control the amount of power output in a very consistent way from a hydrogen fuel cell vehicle. Now, as we think about the future, as we think about, say, light-duty vehicles or our cars and our small SUVs, things like that, that most of us drive around today, if we're only operating them 5% of the hours in a day, then in many cases, battery electric vehicles are the are the best application because they have 95% of the hours in the day to be able to recharge, and they fit the needs of very short distances. However, if we think about vehicles that may be running, say, 16, 18, 20 hours a day, kind of an autonomous vehicle future with Uber traveling everybody around and all those autonomous, never stopping, always operating, then you need, again, that fast recharge or that fast refueling time, and you need to be able to operate for very long periods of time between recharges. That's where hydrogen really fits in. So we already see that. I mentioned dryage trucks is a place where we see that for hydrogen because of the long fueling time. Other applications you see electric. So I see both happening depending upon how you look at the future and what you might see the applications looking like in the future.
Great, thanks, Mark. Our next question is for Jill. Can you delve further into grid resiliency and potential decentralization or localization methodologies on NREL's radar?
Yeah, so we're looking at distributed generation pretty significantly. And this, when we say distributed generation, this is smaller scale generation such as rooftop solar or at household level or commercial scale, and then how that integrates into a larger production. So this could be off-grid systems, it could be community scale systems, or it could be solar or small scale wind that is integrated into a larger grid. So some of the interesting work we're doing, there's really two types. There's a number of projects that we're doing with remote villages, such as in Alaska, the Arctic, and other remote locations that rely currently on diesel. And so we're helping them develop grid systems, mini grid, microgrid systems that can use a variety of clean energy technologies, and helping them understand what the best technologies are and how you model those. The other type that we're looking at is virtual power plants or grid systems that may operate relatively independently, but they're still connected into the larger grid system. And these are interesting because they can operate in a way that they can get power from a larger grid, but they can operate autonomously or by them as an island if there's a disruption in a larger grid system. So a little bit maybe like how the internet works, where you've got lots of resiliency and distributed systems that can work. You can route electricity around in different ways. So yeah, we're looking at a variety of different grid approaches. Interestingly enough, that kind of distributed grid system is really where the electricity grid system started back in the late 1800s, was that way. And so now we're looking at kind of a hybrid system. We've moved to this large power plants, big transmission. Now we're probably going into something in between where you have local generation as well as some larger generation in other locations. So lots of interesting futures to go forward with in the way our energy is created and distributed.
Very interesting, thank you. Our next question is for Ellen. Have we seen any early results or good progress being made from efforts on increasing diversity and inclusion?
So, thanks for that question. I think it's really great. What we have done at NREL is to really take a mindful approach to thinking about which schools have programs and students interested in the disciplines represented at NREL. And so we're in the process, actually right now, we have some research going on with North Carolina A&T, and they have a group of honor students that are under contract with NREL to do a mapping exercise of the HBCUs and HSIs all over the country to figure out which of those schools best align with NREL. In addition, we have a very robust program called GEM Scholars, and Martin Keller was recognized last year for their top award. And that is a program that recruits underrepresented students looking to pursue graduate education in applied science and technology and engineering, that in a lot of connections to NREL. So our cohort of GEM Scholars have grown tremendously over the last few years. And that is also another very concrete program where NREL is heavily involved, from the leadership to all the way to all of the bench science happening at NREL. The other diversity programs we have are related to our internships. We have a number of graduate and undergraduate internships. And as that pool is out there, we make sure that we reach out to schools that have underrepresented groups in them to make that personal connection to those schools, so that the students and the faculty are aware of the awesome research going on at NREL, so that then they can come and work on site either in the summer semester or even in the fall and the spring semester. So we have a lot of different threads out there, but definitely it's something which we see as an important component of the overall university partnership strategy, and I'm extremely passionate about it.
Great. Sounds like some really good progress is being made. Thanks, Ellen.
Mm-hmm.
And now our final question for Martin. How can federal support help all energy technologies advance to achieve a carbon-free grid, including nuclear, along with renewables and energy storage?
So look, I think the federal support for this research is extremely important. And I think there's different stages where you have to go into the research. Look, by definition, if you're a company, a lot of times you will not invest into very high risk technologies. I'll give you an example, for example, in the new solar materials, which is this perovskites. You might have heard about this. The idea is that you might make solar panels in the future like we make newspapers. You can start printing them. But that's very high risk. I mean, there's still a lot of research questions you have to overcome, mostly around stability and how do you make a very thin film and how to bring this up. So it's not very likely that companies at this very early stage will start to change the current manufacturing process and invest into this technology. This said, we started this work a couple of years ago, mostly coming out of funding from Office of Science, and then also now ERE. But then right now, then you're linking with companies, and we're seeing a trend to link with companies in the earlier stage. You're building this, what we call consortia, where you bring the companies in and then you work with them to see what are some of the big issues we have to overcome. You look very early into manufacturing practices. So what I see for the future, we need to fast track technology and how we bring this into the market. And this said, we need to build this public-private partnerships at the earliest stage. But to initiate new ideas, you need federal support. Look, in the nuclear industry, it's very clear, for example, that the first modular reactor now being built in Idaho, it's very hard for a company to start doing this without the support of, let's say, federal funded research. So that's why I think it's very important to have to continued support from federal side, but then also work with industry at an earlier stage.
That's some great insight. Thank you, Martin. Well, that wraps it up for today's webinar. I'd like to personally thank all of the panelists for taking time out of their day to help us create such great digital content, as well as the awesome folks working behind the scenes that I mentioned earlier. As a reminder, this webinar was recorded and will be put up on the ANS webinar website later today. Before we sign off, we'd also like to invite everyone to the next ANS Young Members Group webinar, which will be jointly hosted between the ANS Young Members Group and GAIN, the Gateway for Advanced Innovation in Nuclear, to highlight the work performed by the Nuclear Alternative Project. The webinar, entitled Clean Energy for Industry, Case for SMRs and Microreactors in Puerto Rico, will be moderated by ANS Young Members Group's own Hirsch Desai on June 18th from 1 to 2:30 p.m. Eastern. So thanks again, have a healthy week, and those of you in the US, enjoy your Memorial Day weekend safely.
Thank you.
Thanks everyone.
Thank you, everybody. Bye-bye.
Bye.
Thank you.